Hello everyone. Today we're going to talk about Dalton's law of partial pressures, which addresses the question of what happens to pressure when there is more than one type of gas molecule in your container. For example, most people are familiar with the fact that air is made of a mixture of gases, including oxygen, nitrogen, water vapor, carbon dioxide, and some others. But when we talked about standard pressure and we defined it as the pressure of the atmosphere at sea level, it had one numerical value. Even though there were lots of many different units that you can use to measure that value, it did have one value. So what's going on with this mixture of gases that together present a single pressure for us to talk about? So Dalton's law says that the total pressure of a mixture of gases is equal to the sum of the partial pressures of the individual gases. And what Dalton is saying there is that being in the same container has no impact on the way that the gases cause pressure. This is only really true if the particles don't interact with each other, which makes sense because, as we talked about last unit, gases are much less dense than liquids or solids. So their particles aren't close enough together to bounce off of each other or interact very much. So because of this, pressure in the mixture of gases continues to be related to the total number of particles, as we saw in lab, regardless of the fact that those particles are of different identities. From a calculation standpoint, if the blue gas has a pressure of 2.5 kilopascals, and the red gas also has a pressure of 2.5 kilopascals because it is in the same container and has the same number of molecules. If we wanted to know the pressure of the mixture of those two gases, when we combine them, we would just add their pressures together and get 5.0 kilopascals. Remember that since we are adding, we do need to maintain that tenths decimal place in our product. Okay. So in a sample of air from sea level, which is how we define standard pressure, each component of the atmosphere, the oxygen, the nitrogen, the argon, the water vapor, the carbon dioxide, are contributing their individual partial pressures towards that total 101.3 kilopascals. So if you add up the pressures of the individual types of molecule, you would get the total standard pressure value. Once we understand that the total pressure of a mixture is equal to the sum of the pressures of its components, we can also work backwards. So for example, we're told that a mixture of nitrogen and oxygen has a pressure of 101 kilopascals. If we know that 74 of those kilopascals are contributed by the nitrogen, we can be asked what the partial pressure of the oxygen is. So we just said that the total pressure is equal to the sum of the individual pressures. So if I know the total pressure, if I already know the total pressure and some of the component pressures, then I can subtract out to find my remaining partial pressure. So in this case, I'm going to take my total pressure of 101 kilopascals, and I'm going to subtract out all the known partial pressures. In this case, we only have one, 74. And that will tell me my remaining partial pressure. In this case, the partial pressure of the oxygen. And when I do that, my calculator says that I should have 27 kilopascals remaining that must have been contributed by the oxygen. I do want to check for decimal places since I'm adding and subtracting. I have no decimal places in 101, no decimal places in 74, so I'm ready to present no decimal places 27 as my final answer. We can continue to use this procedure even when we have more than two gases together in the mixture. So for example, A mixture of hydrogen, helium, and neon has a pressure of 133 kilopascals. If the partial pressure of the hydrogen is 53 and the partial pressure of the helium is 33, what is the partial pressure of the neon? So again, I'm going to take my total pressure and I'm going to subtract out all of my known partial pressures. So 53 and 33. And when I put that in my calculator says that it should be 47 kilopascals. Again, none of my numbers have any decimals in them, so I'm ready to present no decimal 47 kilopascals as my final answer to the partial pressure of the neon. Okay, last unit we talked about collecting a gas over water, in particular during the density of a gas investigation. This is a common lab technique, but it does have a problem. As discussed in the Eureka evaporation and condensation video, molecules are constantly escaping from the surface of the liquid water and mixing with the gas that is being collected. When measuring the pressure of a gas collected this way, it is important to remember to subtract out that water vapor pressure from your total pressure measurement. After many experiments, scientists have agreed that the only variable impacting water vapor pressure in this scenario is temperature, and they have created tables where we can look up that relationship. Here's one of them. In this table, the pressure of the water vapor is being measured in millimeters of mercury, one of the units of pressure, and the temperature is being measured in Celsius. You would always be provided a table like this one when you are working on these problems. The pressure unit may vary. Sometimes the water vapor pressure is measured in millimeters of mercury. Sometimes it's measured in kilopascals or torr or atmospheres. But there's always going to be temperature and then the water vapor pressure in the table. These problems work exactly like the other Dalton's law problems that we have looked at, with the added step of you have to look up the partial pressure of the water vapor in this table. So for example, oxygen gas is collected in a graduated cylinder over water. So that phrase is our key word, knowing that we need to use the table. The pressure inside the cylinder is 761.6 millimeters of mercury. If the temperature of the gas is 20 degrees Celsius, which we will need when we are looking in the table, what is the pressure of the collected oxygen? So remember that when we are collecting this oxygen over water, it is not staying as a pure sample of oxygen gas. There is water particles mixed in with that gas sample. So we're going to go to our table and we're going to find 20 degrees Celsius on the table, and we're going to follow across and see that at 20 degrees Celsius, the partial pressure of water vapor is 17.5 millimeters of mercury. So our total pressure, we said, was 761.6 millimeters of mercury. Just like previously, we're going to take our total pressure, we're going to subtract out the known partial pressure, which was 17.5 millimeters of mercury, and that will tell us the remaining partial pressure that must be contributed by our component of interest. In this case, it is 744.1 millimeters of mercury. All three of our numbers have one decimal place, the tenths place, the 0.6, the 0.5, and the 0.1, which means that we are ready to present 744.1 as our final answer for the partial pressure of the oxygen that was being collected. Sometimes you will see the partial pressure of water vapor question asked in an interesting way, and that is in reverse. So for example, scientists collecting gases over water observe a water vapor pressure of 118 millimeters of mercury. What is the temperature of their gases? So because temperature is the only variable that impacts the partial pressure of water vapor when you're collecting over water, you can also work backwards from that partial pressure. So in this case, we are going to go back to our vapor pressure table, and we're going to find 118 millimeters of mercury on that table. And then now we're going to go in the other direction and find out the temperature that matches that point on the table. And in this case, we don't have to do any calculations. We just have to read off of the table that it is 55 degrees Celsius. Their gases are at 55 degrees Celsius, which is quite a warm temperature. All right, folks, so today we talked about Dalton's law of partial pressures. We explained what it was and how to do calculations. Finding the total pressure of a mixture of gases where each of the partial pressures is known, but also working backwards when the total pressure is known to find the partial pressure of the missing component. We also talked about how to deal with calculations regarding collecting a gas over water and how to use a water vapor pressure table to look up the partial pressure of water so that you can do your Dalton's partial pressure law calculation. Thank you very much and have a nice day.